Root Locus Design, Example 2. In this example, we're going to design a PI controller for a plant that will stabilize the plant to a set point, whatever that is, within 2 seconds. And it will have an overshoot of less than 5%. The overall system is shown in this diagram that we have here, and we've got the control and the plant in cascade, and then we've got the negative feedback through H. On the first page of our notes, I give you a table and I give you the model for the PI controller, and you see it's got a 1 over S term, and that represents the integral part of it, and it also has a proportional part of it through Kc. So unlike the first example we did, we only have 2 constants to find. That would be Kc and A. H is equal to 1, and the plant is modeled simply as 16 over S plus 2 times S plus 8. So we'll start out by finding the closed loop transfer function pole location, P. The last example, this was what I referred to as S. So one of the things that was given in this problem was the settling time, and that was 2 seconds. And so that's going to be equal to 4 over sigma, which is 4 over zeta omega n. So either one of those formulas works here. We were also given an overshoot, m sub p, equal to 5%, which of course is 0.05. So we're going to use that to find the closed loop pole locations. Now, in the previous problem, we were just given this, S equals negative 0.25 plus or minus j 0.25. And that was just provided to us. We were given no reason why that was chosen, but it was given to us, and so we used it. In this case, we're starting with these 2 bits of information, the settling time and the overshoot, and we're going to use that to actually find this point. And again, in our case, we're calling it the point P, not the point S. So I'll remove that and we'll work through how we do that. So the first thing we do is we note that m sub p is equal to e to the minus zeta pi over the square root of 1 minus zeta squared. And ultimately, we will go through some algebra and we'll find out that zeta is going to be equal to 0.6906, and that is equal to the cosine of beta, and beta is going to be equal to about 46 degrees. So because that's so close to 45, we're just going to say 45 because that's an easy one to work with. So yes, it is 46, but no one can tell the difference between a 46-degree angle and a 45-degree angle. So we're going to use that. And I'm going to go ahead and indicate to you this in a pole zero map. I've already pre-drawn that. Here it is. So here's our beta. Here's our angle beta. And sigma we can get from right here. So sigma is going to be equal to 4 over 2, or just plain 2. So that distance from here to here is equal to 2, and so with a 45-degree angle, this point right there is going to be a negative 2. Beta equals 45, so this point that's right there, we're going to call it the point P, is going to be equal to 2 times j, which means that there's another point at negative 2j. So the point P is equal to minus 2 plus or minus j2. Okay? So now I've skipped a lot of steps here, and I did that because we've done this before, but I will provide those to you in this next copy paste that I'm going to do for you. And go ahead and do that. Get rid of all of these things so that you can see that. But definitely you can simply follow this algebra to find the value of zeta equals 0.6906, which is right here. So now that we know that, we know these values, we know the value of P, again, negative 2 plus or minus J2. We can continue on in this problem where we started from the previous problem. So so we're going to follow the same practice that we did before, and what we see is that for this system we have first we're going to write the KGH, okay, and that's going to be equal to G sub C, so KC times S plus A over S times G, times GP, so this KG is going to be equal to GC GP, and so that's going to be 16 over S plus 2 times S plus 8, and H of course is 1. So we can see we have poles here at S equals 0, S equals negative 2, and S equals negative 8. And we have zeros at negative A. We also note that the constant, the root locus constant, K, is going to be equal to K sub C times 16. So that's where we start out, and we'll take these values and we'll put them inside of a nice chart, and I've already drawn that up, so I'll show you that now. There we are. So here's our point P. It's at negative 2 plus J2. We've got a pole at 0, so that's the 0. We've got a pole at negative 2, and we've got a pole at negative 8. Okay? We got our point P, which is a 45-degree angle from the origin, so we've got a few lines to draw and some notation. So let's just go through that. So for the pole at 0, It's right there, and the line goes right up to 2p. The distance is d1, and the angle right here, that's theta 1. Okay? And obviously it's a 45-degree angle, so that's going to be theta 1 is just by observation is going to be 135 degrees. Then we've got theta 2, which is for this pole that's right here. That one's the easiest one of all. It's just straight up 90 degrees. So theta 2 is 90 degrees. And I'll write these in a little nicer form here in a moment. And then we got theta 3, which is right out here, and that's from the pole at -8, 2p. We've got a distance d3, the angle theta 3. So we've got all our pole distances and angles all marked. And then we can go ahead and show the zero distances. So we have a 0 here, and that's going to be our -a. Now, again, just like the last one, we don't know where this is located. We'll find out in this problem. But we have gone ahead and we know that this distance of this is going to be d, and the angle, that internal angle there, is phi. Okay? So now that we have that, we can go ahead and I can go ahead and write the angle condition. Now, as you should remember, the angle condition is going to be the polar angles minus the zero angles equals 180 degrees. So the angle condition is going to be theta 1 plus theta 2 plus theta 3 minus phi, so minus the zero angles, equals 180 degrees. So we know theta 1, 135, we know theta 2, it's 90, and that just leaves theta 3 to figure out. So theta 3 is going to be, again, it's this angle right here. So I'm going to erase some of these lines so that I can show this a little bit more clearly, so that it's not confusing. Sorry about that. I wanted to leave that theta 1 there. So the angle, or the triangle that we use for that, is going to be the hypotenuse, the opposite side, and the adjacent side. So theta is going to be the inverse tangent of the opposite. So that's going to be this distance right here. And that should be very straightforward. It's just going to be equal to 2. It's the distance of that leg. And then over the adjacent side. Now the adjacent side is going to be 8 units minus 2, so 6 units total. And so theta 3 is going to be 18.4 degrees. So we've got theta 1, 135, plus theta 2, 90, plus theta 3, 18.4, minus phi equals 180. Do a little algebra there, and we find out that phi is equal to 63.4. degrees. So I don't need to redraw this, but here's the angle we're looking at, and it's probably closer, it's where I placed it. It probably is farther to the left than I placed it. That phi is probably, if it were at 4, it would be 45 degrees. I put it between -4 and -5, so maybe like 50 degrees or so. So it may not be in quite the right location, but it's close enough. But now that we have that, we can go ahead and figure out the actual location of A. So so I'm going to go ahead and I'll use a different. Well, first of all, let me erase this stuff again, and let's look at the angle for phi. So I'll use this orange here. So this is the triangle we're going to use. So for A, the adjacent side, so this distance right here, so the adjacent side is going to be equal to, remember, tangent of theta, tangent of phi is equal to the opposite over adjacent. So the adjacent side is the opposite over the tangent of the angle. So tangent of 63.4, and the adjacent, or the opposite side, which would be this right here, that's going to be just plain old ordinary 2. So the adjacent side is going to be actually equal to 1, turns out. This distance between the origin and A, well, maybe I'll just put it like this. So so what this says is this distance is 1 unit plus 2 units, so it's going to be 2 plus 1, so that's 3, and it's a negative A, so negative A is equal to -3. So actually, I really kind of goofed up. I should have put it right there, and the leg would be right there. So, so the opposite direction of what I actually said a couple of minutes ago. But there we've got now the value of A, and now we need to find the value of K sub C. So let's look at root locus gain, and now we're going to use the distance formula. And the distance formula says that the root locus gain K is equal to distance d1, all the polar distances multiplied together. So d1, d2, d3 divided by the 0 distances, which is d. So that's going to be, for d1, it's the square root of 2 squared plus 2 squared, d2. That's actually, we can still write it, but it's just going to be 2. So 0 squared plus 2 squared. And then d3 is going to be 6 squared plus 2 squared, square root of that. And then all over d, which is going to be the square root of 1 squared plus 2 squared. And that is going to give us, actually, the value is going to be 16. So that, if you remember from earlier, we said that the root locus gain, K, is equal to 16 K sub C. So therefore, K sub C equals 1. So if I go back up here to G sub C, We found the value of A. The value of A is 3. And we found the value of KC, it's just 1. So G sub C is going to be equal to 1 times S plus 3 over S. And we're done. So if we use a controller, a PI controller, with those parameters, Kc equals 1 and A equals 3, then the plant will stabilize in 2 seconds and it will have an overshoot that's less than 5%. And again, we used the 2 seconds and the overshoot to help us determine the location of the desired pole location, the value that we called P. Once we do that, we use the angle condition, the distance formula, to find the values for K sub C and A, and we are able to solve the problem. In other words, design the controller.